Hello, everybody. Welcome back to the Explore Expander Bootcamp. We've got another workshop today. Just while people enter the session, I'm going to invite our speaker to the stage. Let me just do some housekeeping whilst everybody gets connected. Remember to post all your questions in the chat. We will do a Q&A at the end of the session, where you can have your questions answered. Welcome, Yupeng. How are you doing today?
Hi, good. How are you?
Yeah, good, thank you. Would you like to just share your screen and get set up whilst I just cover the last of the housekeeping?
Yes.
Remember to post your questions in the chat, guys. The link to the hacker pack should be displayed in the links tab at the bottom, everybody, and you can use this to find the recording, which should be posted in the next 24 hours or so. But yeah, I think that's everything from me. So let me just introduce our speaker for today. So this is Yupeng Zhang from University of Illinois, and today he's going to be giving a workshop on GKR and Sumcheck Protocol. Great, your screen is visible and looks great. So I think I'm going to hand straight over to you. I'm going to hop off of the stage, over to you.
All right. Thank you for the introduction, and thanks for having me to give this talk at the bootcamp. So I've actually been working on this field for quite a while, and then did some research on Sumcheck and GKR since my PhD. So it's glad to see that there are so many interest and even some product industry using these protocols. Yeah, so the topic of this talk is on Sumcheck and GKR protocol. So I believe in previous lectures, for example, Dan and Jens already introduced the formal definitions of zero-knowledge proofs and zk-SNARKs. So here I'm just going to go over these basic settings very quickly, and I refer the audience to the previous lectures for formal definitions and more details. So we're talking about the zk-SNARK, which is a cryptographic primitive that allows a prover to prove some statements about the secret data to the verifier. So this relationship is really modeled as a public computation C on the secret data W and public input X and outputting Y. And the verifier is able to check the correctness of this claim. And there are three basic properties. So correctness means that if everyone's honest, then the verification always accepts. And soundness means that the cheating probability of the prover is negligible. You can't return a fake statement. And also zero knowledge means that this proof leaks no information about the secret witness W beyond the fact that the computation is done correctly. And also there are two more important properties in zk-SNARK. So this S stands for succinct, meaning that we want the proof size to be much smaller than the size of witness and the computation. And this N stands for non-interactive. There's no interaction between the prover and verifier. But usually this one, you can actually compile interactive proof into a non-interactive one using the Shamir transform. And this zk-SNARK has become a very active area in both academia and industry in the recent years because of its great applications in many of the domains. So the most notable one is the blockchain applications. For example, you can use zk-SNARKs to build privacy-preserving cryptocurrencies, and then zk rollups, zk EVM, and zk bridges for cross-chain transactions. And there are also papers and products for zk identity, decentralized finance, and so forth. And beyond blockchains, you can also use it to prove the correctness of machine learning computations. For example, there are some recent work on zero-knowledge inferences, training, fairness, and so forth. And you can also use them for photo authenticity. And then there are papers on zero-knowledge mailboxes proving the compliance of encrypted data in internet packets. And there are also several companies building so-called zk-VM, proving the execution of any programs in these virtual machines. Again, I believe there are many great talks before and after my lecture, so I will leave more details to these talks and the presenters. So the main focus of this talk is actually on the zk-SNARKs based on Sumcheck and GKR, which is actually the core technique underlying the expander system. So this talk will be a little bit technical. So I will present the full details of the Sumcheck protocol and the GKR protocol. Okay, but I'm going to start with a brief kind of overview of the history and development of the Sumcheck protocol and the GKR protocol first. So the Soundness protocol was actually proposed in this seminal paper by Lund, Fortenau, Karloff, and Nissan in 1992. And this gives an interactive proof protocol for the Soundcheck problem, which I'm going to formally define later in the lecture. And this was actually a very impressive protocol and very important result in the complexity theory and in class of interactive proofs. For example, soon after this paper, Adi Shamir had great results proving that IP equals to P space. And then Soundcheck was also used as a building block in the great PCP theorem and so forth. So it's a great breakthrough in the theory side. But the focus of my talk is more on the apply side. And the next big advancement is this GKR protocol, named kind of by the initial of the authors, Goldwasser, Kalai, and Rothblum in 2008. And here I'm actually referring to the conference paper in 2008, just to give you a clear timeline of the development. So this one is a delegation of computation protocol for any layered arithmetic circuit. Again, I'm going to explain the details later in the lecture. But this actually supports verifying the results of layered arithmetic circuits with a succinct proof size and verifier time. So then after this GKR paper, there were a lot of papers trying to improve the prover efficiency of the GKR protocol. So in the original paper, the prover time was actually polynomial time, or if you implement naively, is cubic in the size of the circuit. So this is clearly not practical. But of course, the original paper was mainly of a theoretical interest. So then in 2012, there was a paper by Cormont, Mizameter, and Thaler improving this prover time from cubic to quasi-linear. It's order of L log, which is actually very close to optimal. This is utilizing kind of the sparsity of these equations involved in the GKR protocol. And then after that, there are many papers trying to improve the prover time for different types of circuits, including some of my prior work. So it can actually make the prover time very close to linear for structured computations and data parallel circuits. And for some special computations like matrix allocations and addition trees and multiplication trees, you can actually make it strictly linear. And eventually, in our earlier paper in 2019, we proposed a system called Libra, which gives you a strictly linear time prover for the GKR protocol. And this is actually optimal because asymptotically, this is the same as evaluating the circuit. So that's the best you can do. And concretely speaking, the constants are actually very small. So the practical performance is actually outstanding. Okay? And after this paper, I'm also aware of some recent developments on very fine-grained optimizations in, for example, some of these papers. You can actually do Soundcheck protocol while only pay for the cost of non-zero elements. And the zero elements in the equations are free. So this is some additional optimizations. And I also want to mention that there's another work in one of our earlier papers. So we can actually generalize the intermediate representation of the GKR protocol. So all of these prior works work on layered circuits, but you can actually support general circuits with arbitrary connections without any overhead on the prover. So the prover time remains linear in the size of the general circuit. So this is kind of the development on the Soundcheck and GKR side. But Soundcheck and GKR protocol are actually not SNARKs on their own. Right? So in these protocols, it's more of a delegation of computation. You don't have any secret witness from the prover side. All the input of the circuits are known both by the prover and the verifier. And the verifier is just trying to delegate this computation to the prover and verify the correctness. but you can actually combine Sumcheck and GKR with a so-called polynomial commitment scheme to get zk-SNARKs. And this idea was first initiated in my earlier paper called vSQL. So here I'm switching to the names of these SNARK systems for better references. So in this vSQL paper, we actually proposed the SNARK based on the GKR protocol and polynomial commitments. And later in Herax, the authors made it zero knowledge and also removed the trusted setup from the construction. And also concurrently, there's a ZK vSQL paper making it zero knowledge. And as I mentioned in Libra, we made the prover time linear. And then in Virgo, we also removed the trusted setup using some ideas from the Fry literature. And then this one is supporting the general circuits instead of layer circuits. And in terms of the Sumcheck protocol only, there are also many SNARK schemes using the Sumcheck protocol as an important building block. So they're not using the GKR protocol in the layer by layer reduction sense, but Sumcheck protocol is actually a very common building block because of its powerful functionality and outstanding efficiency. So there's a kind of popular SNARK protocol called Spartan with great prover efficiency. And also there are Breakdown and Orion using linear time encodable error current codes combined with Sumcheck protocol to build SNARKs. And then later there was a hyperplonk, a SNARK for plonkish circuits. And then more recently there are papers called Basefold and Blaze. So their contributions are more on the multivariate polynomial commitments based on error current codes. But nevertheless, they're using Sumcheck as an important building block to build the SNARKs. And also some special protocols worth mentioning is there are popular protocols called lookup arguments in recent years. They're actually very important to improve the prover efficiency for general purpose SNARKs because you can actually support lookup operations efficiently. And there are very good lookup arguments with outstanding prover efficiency based on Sumcheck and GKR protocols. For example, there was a logup paper based on Sumcheck, and the logup GKR is using the GKR protocol explicitly to improve the prover time. And then earlier last year, there was a Lasso paper using multi-linear polynomials and Sumcheck protocols to build lookup arguments. Okay? So as you can see here, Sumcheck and GKR are really important protocols in the literature of interactive provers and SNARKs. And there are many zk-SNARK schemes based on them. So then what's the main reason for this constructions using Sumcheck and GKR protocol? I guess the main advantage I want to say is, so in Sumcheck protocol and GKR protocol, we are using this multivariate polynomial representations for the constraints and the SNARK schemes. And compared to those schemes based on univariate polynomials, such as Groth-16, Planck, and Fry, the advantage is on the prover time, because while using multivariate polynomials, we don't need to pay for the cost of fast Fourier transform, FFT. So because of that, oftentimes you can actually achieve linear prover out of n versus out of n log n for those univariate polynomial-based schemes because of FFT. But the drawback is usually on the proof size. So because of this multi-round nature of Sumcheck and GKR, the proof size is usually, there is an order of log n overhead in these schemes. Of course, the exact numbers and complexities really depends on the constructions of different systems, but these are kind of the general trade-off between the prover time and proof size for the Sumcheck-based and GKR-based protocols. Okay, so that's really a very quick and brief overview for the literature of Sumcheck and GKR and zk-SNARKs based on them. So in the next part, I'm going to formally present the Sumcheck protocol, which is the most important building block in many of these schemes. So in order to understand the Sumcheck protocol, first I want to spend some time to further explain this multivariate polynomials. Okay? So a k-variate polynomial is a polynomial taking k variables, x1 all the way to xk, and it's defined over a finite field, fp mod p. Okay, so all the coefficients and evaluations domains are defined over fp. And it's actually better to show it with an example, right? So here's a bivariate polynomial, fx1, x2. You can see that there's a constant term 5, and you have the individual terms 4x1 plus 3x2, and you can have cross terms 2x1, x2, and you can also have higher degrees, x1 times x2 squared. So that's a two-variate bivariate polynomial. And to categorize these multivariate polynomials, I'm going to introduce a parameter called variable degree d of a multivariate polynomial. So this is defined as the maximum degree of this multivariate polynomial in each variable. So for example, in this bivariate polynomial, the variable degree is 2 because the degree of x2 goes up to 2. So that's the maximum degree of each variable. Okay? And you may also heard of the term total degree, which counts the sum of the total degrees of each monomial in the multivariate polynomial. And there are some relations between the variable degree and the total degree, but I'm going to use the variable degree for better explanation of the Soundness protocol in this talk. And there is actually a very important special case of a multivariate polynomial that is called multilinear polynomial. And the definition is very simple. It's the variable degree is just 1. So the degree of each variable can at most goes up to 1. So that's why it's called multilinear. So clearly, this example is not a multilinear polynomial because the degree of x2 is larger than 1. And the example of a multilinear polynomial is here. You just remove this term. That is 5 plus 4x1 plus 3x2. And then you have the cross term, but the degree is of each variable is only 1. Okay. So then the next question is, what's the size of a multivariate polynomial? Okay, so to define the size, you are basically counting the number of coefficients, or equivalently, number of unique monomials in the multivariate polynomial. So we're going to start with the simplest case of a multilinear polynomial. And here I'm going to show you a very interesting way to count the size or count the number of monomials. Okay? So this is actually in the way of a binary tree expansion. So to start, how many monomials are there for a polynomial with a 0 variable? It's just a constant polynomial, and the monomial there is 1. So the size is 1. And what about a univariate polynomial, a polynomial with 1 variable? So the way to count it is you are going to multiply either 1 or x1 to the previous round. So you get either the constant term or the x1 term. And there's nothing else because the degree is at most 1. So you have 2 monomials and the size is 2. And similarly, how many monomials are there for a multilinear polynomial with 2 variables? You just multiply either 1 or x2 to the previous tree here. Right? So you get here 1 and x2, and here you get x1 and x1, x2. So each one, you can actually get a unique monomial using this binary tree expansion. And the size of the multilinear polynomial with 2 variables is actually 4. And you keep doing that, you can actually multiply either 1 or x3 to the previous subtree, and then you can actually get 8 unique monomials in this way. So as you can see here, basically there's a very nice binary tree expansion structure for the number of monomials in the multilinear polynomial. And the general form for this is the total size of a multilinear polynomial capital N equals to 2 to the k, or k is logarithm in n. So that's the size of a multilinear polynomial. And this approach also generalizes very nicely to just a general form of multivariate polynomials. So for example, if your variable degree is 2, then instead of a binary tree, you just have a ternary tree where the expansion factor is increases. So from 1, you can either have 1, x1, or x1 squared, and so on and so forth. So for a multivariate polynomial with 2 variables and variable degree 2, you have 9 monomials and 9 coefficients. And the general form for this multivariate polynomial is capital N, the size equals to d plus 1 to the power of k. Okay, so you can actually calculate this by reasoning that each variable can either appears in degree 0, 1, 2, all the way to d. And then there are k variables in total, and each combination gives you a unique monomial. So in total, there are d plus 1 to the power of k possibilities. Okay, so that's the size of a multivariate polynomial. So with a better understanding of the multivariate polynomials, I'm ready to actually present the Soundness problem. So the Soundcheck problem is saying that given a multivariate polynomial, we are interested in evaluating the sum of all its evaluations over all possible binary inputs. Okay, so we want to evaluate f000 all the way to f1111 and then sum up these evaluations for some reason. Okay? And then we call this one as the Boolean hypercube. It's kind of the Boolean hypercube in multi-dimensional space. And then again, using examples, right, for the same multivariate polynomial, you can see that this problem is just very well defined, right? You can evaluate f00. You just substitute x1, x2 by 0, 0. And what's the evaluation? It's just the constant term, 5. Okay? And you can do f01, that gives you 5 plus 3, that's 8. And then f10 gives you 9, f11 equals to 14. And you sum them up, the total summation is 36. So it's a well-defined problem with the answer of a single value representing the summation. Okay? So that is the Soundcheck equation or Soundcheck problem. So what's the complexity of computing this sum? Okay? So clearly there are 2 to the k evaluations in the summation because you're trying to evaluate all possible binary inputs, right, from all zeros to all ones. And there are k variables. So in total, there are 2 to the k elements in this summation. The time to compute each summation actually highly depends on the form of the multivariate polynomial. And I'm not going to calculate the details here. I'm just going to use this capital T to denote the time of a single evaluation for this multivariate polynomial at any point. Okay? So then with these 2 numbers, the total time to compute the sum S is 2 to the k times T. Right? You have 2 to the k evaluations and T to evaluate each evaluation. So you can see that this is actually a kind of exponential time in k, the number of variables. Okay? So now let's say that the verifier is actually is very lazy. I'm not going to compute anything that is 2 to the k times T. I'm not able to compute this summation. So how about we delegate this computation to a prover? We're going to ask the prover to return a claimed summation S star, and then can we figure out a way to efficiently check whether this S star is equal to the real summation of this multivariate polynomial or not. So that is the Soundcheck problem. Right? And then the Soundcheck protocol actually gives you a way to do this. It's an interactive proof to check the summation of the Soundcheck equation. And then naturally satisfy these 2 properties. So completeness says that if everyone's honest, then the verifier always accepts. And the soundness says if the prover is cheating, if you're returning a wrong summation S star that is not equal to S, then the probability of verifier accepting this answer is less than or equal to negligible. It's 1 over 2 to 128, for example. And of course, in order for this product to make sense, we also want the proof size and the verifier time to be faster than evaluating this Soundcheck equation locally. So that is the setting of the Soundcheck protocol. So how can we do that? Okay, so here's the idea of the Soundcheck protocol. So it proceeds round by round. Okay, so it's a kind of a recursive structure of a protocol. And then in each round, we are going to reduce this Soundcheck problem into a smaller instance, into another Soundcheck problem for a smaller polynomial. Okay, so let's see how we can actually do this. So in the first round, the prover is going to send a univariate polynomial in variable x1. So that is f1, x1. And this univariate polynomial is defined by this summation. But you can see here that the prover is actually summing over all other variables, b2 all the way to bk, except for x1. Okay? And that will give you a univariate polynomial in x1 because everything else there's a summed over. It's evaluated at either 0 or 1. Okay? And then by the definition of this univariate polynomial, you can see that if the prover is honest, I'm actually describing the honest execution of the protocol, then the summation S should equal to f10 plus f11. And that is because the prover has already summed up everything else, and there's only x1 left. So you can actually sum f10 plus f11 on your own, and that should equal to the total sum. Again, using the same example, right? So this is the multivariate polynomial. So you can actually evaluate fx1, 0. You just substitute x2 by 0. And this should equal to 5 plus 4x1, because x2 just disappears from this polynomial. Similarly, you can evaluate fx1, 1 by substituting x2 by 1. And this equals to 8 plus 6x1. Then by the definition here, f1, x1 should equal to the summation of these two polynomials, which is 13 plus 10x1. So again, you can see that this is a univariate polynomial in x1. And then the same applies if you have more variables than this. You're just summing over all x2 all the way to xk. Okay? And then you can also see that if you evaluate this univariate polynomial at 0 plus the evaluation at 1, it equals to 36, which is the total sum. And this is actually by the definition of the polynomial. It's not a coincidence. Okay? So that is the first round, half of the round for the Soundcheck block. Okay? So after that, now the verifier holds this f1, x1. The next step is the verifier is going to pick a random number r1 that is sampled uniformly from the finite field. And then the verifier is going to evaluate this univariate polynomial f1 at the point r1. So this f1, r1 is a single value. Okay? And then the verifier is going to send this r1 to the prover side. And in this way, we can actually reduce the problem to a smaller instance. And why is that? I'm going to write out this f1, r1 for you. Okay? And f1, r1 just equals to the summation of b2 all the way to bk, f r1, and then b2 all the way to bk. So you can see that this is exactly the copy from the definition of f1, x1 by replacing x1 by r1. Okay? And this is also a Soundcheck equation, right? You're summing over b2 all the way to bk. And this is one variable less because x1 has already become r1. It's a random evaluation, so there's nothing to sum on. Okay? And this is usually called x1 is bounded by r1 in the literature. Okay? So with that, so literally you're summing over a different polynomial here, right? So this is a polynomial with one less variable, but is related to the original multivariate polynomial f. Okay? And the check here is whether this f1, r1 is correctly computed or not. Okay? So of course, we need to reason about the soundness, which I'm going to do it after presenting the protocol, but this is a reduction to a problem of a smaller size. And again, why this is a smaller problem? We call the binary tree expansion view of this multivariate polynomial, right? So if you have one less variable, so there's no x1 in this tree, then you end up with this left subtree with only x2 and x3, and the size is half of the size. So in this way, you're shrinking the problem into half of the size of the multivariate polynomial with one less variable in this first round of the program. Okay. So if you understand this part, then we're just going to do it recursively in the following rounds. So in the second round, the prover is going to send the verifier another univariate polynomial in the variable x2. So that is f2, x2 that is defined by summation of all the remaining variables, b3 all the way to bk. We leave x2 as the variable, and the x1 is bounded by r1. Okay. And then again, by the definition of this polynomial, if this polynomial is computed correctly, then f20 plus f21 should equal to f1, r1. And you can check this easily by this definition of these two equations. And that's the verifier's check in this round. Okay. And then the verifier check is going to pick another random number r2 and evaluate f2, r2 and send this random number r2 to the prover again. So in this way, we're reducing this claim to f2, r2. And if you write it out, which is another Soundcheck equation for a smaller polynomial with k minus 2 variables. Okay. So then you just keep going, doing this round by round. And the general form for round I is in the previous round, the prover receives ri-1 from the verifier. And then the prover is going to send a univariate polynomial in variable xi. And this is defined as summing over all the remaining variables, bi plus 1 to bk, leave xi as the variable, and then all the previous variables are bounded by random numbers, r1 to ri-1. And again, if this is computed correctly, the verifier should check that fi0 plus fi1 equals to fi-1 evaluated at ri-1. Okay? And eventually, you will just do it all the way to round k. And here's what's happening in the last round. There's actually an additional check. So in the last round, this is the form for the univariate polynomials. And you notice here, there's nothing else to sum up, right? So there's no more variable. So fkxk is just defined as this multivariate polynomial with all the previous variables in replaced by random numbers, and then there's a xk as variable. And then you check that fk0 plus fk1 equals to fk minus 1, rk minus 1. In the last step, there's one more check. The verifier is going to evaluate this fkxk at another random point rk, and then check that if it is the same as the original multivariate polynomial f evaluated at r1, r2, all the way to rk. So that's last check is actually also very important. So that completes the description of the Soundcheck protocol. Okay. So then we're just going to briefly reason about the completeness and soundness. So completeness is basically holds by design. So basically, I was basically explaining the completeness of the protocol. Right? So by the definitions of these polynomials, all these verifications should pass if the prover is honest. And for soundness, this is actually a very elegant reasoning of the soundness of the protocol. And here I'm just going to sketch the idea, but I highly recommend you to take a look or do it as an exercise. This is a very nice reduction. Okay? So similar to many cryptographic protocols, we usually do the proof by contradiction. Right? Suppose that the prover is cheating, so it is returning a wrong result S star that is not equal to the real sum S. So then the way we're going to do the reduction is we're going to do the conditioning on whether the first univariate polynomial f1 star is correctly computed or not. Right? So is the prover still cheating on f1 star or not? And there are two cases, right? If f1 star is correctly computed, it's actually not possible to pass the check, because if f1 star is the same as f1, the real univariate polynomial in the first round, then f10 plus f11 should equal to the real summation, which is different from the fake summation. So this check cannot pass, right? So that leaves us with only possibility. f1 star is also fake. It's different from the real f1 x1. Okay? So what are we going to do in that case? Go to the next round. Okay? So in the next round, we know that f1 star is different from f1. So then we are going to do the conditioning on whether f2 star is correct or not. Is the same as the real f2 or not. Okay? And then you can actually see this recursive reduction structure, right? So if yes, then it means that f2 star is correctly computed, which means f20 plus f21 should equal to the real f1x. And then you are checking this relationship at a random point r1. But f1 star is different from f1. Okay? So then what's the probability of two different polynomials agreeing on this random point r1? That probability is actually very small. It's d over the size of the finite field. And this is actually the famous de Miller-Lipton-Schwarzschild lemma, okay, saying that because a non-zero polynomial can at most have d roots, so the probability of picking a random number being the roots is negligible. Okay? So that shows that if f1 star is also fake, then you should keep cheating on f2 star, the prover. Right? Otherwise, you can't pass the check with a good probability. Okay? So then what we're going to do, go to the next round. So following this reasoning, you can see that if S star, the sum, is fake, then the prover has to cheat on f1 star, f2 star, f3 star, all the way to fk star. And eventually, in the last round, the verifier is checking that this fk star rk equals to r1 all the way to rk, the evaluation of that multivariate polynomial. Again, by the Schwarzschild lemma, if this fk star is different from the real answer, this can only happen with negligible probability. So that completes the whole reduction of the Soundcheck protocol and guarantees that the answer S has to be correct. Okay, so the total soundness error is k plus 1 times d over the field of the size of the field. Okay, so that's the idea of the Soundcheck protocol. So finally, about the Soundcheck protocol. So what about the complexity? So the performance, the prover and the verifier. So the number of rounds is exactly the same as the number of variables, that is k, which is logarithm in the size of the multivariate polynomial. And the total communication is k times d, because in each round you're sending a univariate polynomial in each variable, and then a univariate polynomial can be uniquely represented by d plus 1 coefficients. So in total, this is order of k times d, and if d is a constant, for example, multilinear polynomials, then the proof size is order of log n. And the verifier time is also order of log n, plus the time to evaluate this multivariate polynomial at a random point in the last round. Okay? And recall that the total time to compute the summation is 2 to the k times t, which is actually quite large, is capital N times t. But using the Soundness protocol, the verifier can actually delegate this task to the prover with a proof size that is only log n, and then the verifier time is order of log n plus a single evaluation. So that is the powerful Soundness protocol to delegate this computation. Okay. So then the last piece of the puzzle is the prover time. Right. So what is the prover time for this Soundness protocol? So this there is actually an optimal algorithm for proving the Soundness on multilinear polynomials. This was proposed by Justin Thaler in his paper in 2013, and the technique is called dynamic programming. Okay. So it turns out if the prover has access to the evaluations of this polynomial over the Boolean hypercube, all the binary inputs, then the prover can actually use this array to generate the univariate polynomial in the first round of the protocol in time linear in the size of this array. Again, I'm not going to show the details, but you can actually sit down and derive the equation. You can easily see that you can actually do that through a simple scan of this array. But more importantly, after receiving this randomness from the verifier in round 1, the prover can actually update this array by combining 2 elements into 1. And that will give you an array of half of the size. And this is actually the evaluation of a smaller polynomial over the Boolean hypercube. And using the new array, the prover can generate next message in time linear in the size of this new array, which is half the size of the previous array. Then the prover can keep doing that recursively, right? Cut the size of the array by half and then generate the next message until the array shrinks to a single element. So in this way, the prover time is actually order of n plus n over 2 plus n over 4 and so forth, which is linear in the size of this array, which is also linear in the size of the polynomial. Okay, so that is the prover algorithm for multilinear polynomials. And this idea also generalized to any constant number of products of multilinear polynomials in the summation. Okay, here you can see that there's a summation of f times g, but you can actually initialize 2 arrays and then update them separately and then combine all the elements to generate the message in each round. So you can still have the strictly linear prover time. And this is actually a very important building block for the GKR protocol with optimal prover time. Okay. So with that, here's a quick summary for the Soundness protocol. So Soundness is an interactive proof for the Soundness problem, and you can actually make it non-interactive via the Fisher-Trimble transformation. And then we have a linear prover time, logarithm proof size, and verifier given the access of a random point of the evaluation of the multivariate polynomial. And the soundness is merely based on this Rho-Zippo lemma. So it is unconditionally secure without any cryptographic assumption. So that's why it's an amazing result in the literature, because you can only see a few protocols in cryptography that is not relying on any cryptographic assumptions. Okay, so that's the part for Soundness. Let me see the time. Okay, so then in the remaining about 10 minutes, I'm going to also talk about the idea of the GKR protocol very quickly. Okay? So GKR protocol is trying to build a delegation of computation for arbitrary computations, right? Instead of just this very special Soundness equation. Okay? And of course, we want to satisfy correctness and soundness, meaning that if everyone's honest, you always pass the verification, and then if the prover is cheating, the probability for passing the verification is negative. And a very common way to support arbitrary computation in cryptography is to model the computation as circuits, right? Because circuits are universal. So in principle, you can support any computations that can be done on computers. And the intermediate representation of the GKR protocol is using layered arithmetic circuits. So it's a circuit with addition gates and multiplication gates modulo prime number p. And then this circuit is layer by layer, meaning that the gates in one layer can only connect to the previous layer. Okay, and then here I'm kind of laying it upside down, but you will see the reason soon when I present the GKR protocol. And so we are going to call the output as layer 0 and then the input as layer D. So in total, there are D layers in the circuit. And the key idea of this GKR protocol, if you only remember like one sentence about GKR protocol from my talk, is we are just going to try very hard to write the output Y as a Sumcheck equation of the input X. And why are we doing that? Because we know Sumcheck protocol. Right? Just run Sumcheck protocol on this Sumcheck equation, then you can actually get delegation of computation. Okay, so that is the key idea of this design of GKR protocol. But it is actually very non-trivial to do it, and that's actually the key contribution of this GKR paper. Okay, so in order to do this, we need to actually define some actual terms and notations. So here's this layered arithmetic circuit, and I'm going to use capital N to denote number of gates in each layer, assuming that number of gates is the same. But this is actually just for ease of presentation. There's no requirements in the protocol. Okay? And the depth of the circuit is capital D. So then we're going to label the wires or the inputs using the binary indexing. Okay? So for example, the input is A00, A001, A010, A011, so forth. Okay. Then how many bits do we need to label the gates? Well, clearly this is k equals to log n in base 2, right? So that's how many bits to represent a number between 0 and n minus 1. Okay. So then the next important step is we are going to define a multivariate polynomial, VD, using the input. We want this multivariate polynomial to agree with this input on all the binary inputs. So VD000 should equal to A000. VD001 should equal to A001, and so on and so forth. Okay. So then clearly, how many variables are there for this multivariate polynomial is the same as the number of bits, which is k equals to log. Okay. And recall, if this polynomial is multilinear, how many coefficients do we have? This is 2 to the power of k, which is exactly n. So because of that, you have a linear kind of system. You have n constraints and n coefficients to decide. So because of that, you should have a unique solution for VD. Right? And this multilinear polynomial is actually called the multilinear extension of this array or an input function. Okay, and there is actually a closed form to compute it, but I'm not going to show it here. Okay, so that's how we define this multilinear polynomial using this multilinear extension. And similarly, we are going to use the values in each layer of the circuit to define a multilinear polynomial. So we have VD minus 1, VD minus 2, and so on and so forth. And why are we doing that? Well, because of the key idea, right? We want to represent the output as a Sumcheck equation of the input. So once we do that, you can see that there is actually a relationship between two polynomials defined by two consecutive layers, simply because they're connected by the gates in the circuit. Right? So here, for example, there is a multiplication gate here. By the way we're labeling these wires, this means that V00, which is the value on this wire, should equal to V100, which is the value here, times V101, which is the value here. Right? So that is the definition of a multiplication gate. So we're getting there, right? But this equation is not a Sumcheck equation. So we should try a little bit harder to make it a Sumcheck equation so that we can apply the Sumcheck protocol, right, between VI and VI plus 1. So can we do that? Yes, and here it is. Okay, so this is a kind of a seemingly complicated equation proposed in the GKR paper. That is actually the major contribution of the paper, right? But I'm going to explain this a little bit. So you can see that it seems like it's quite ugly and complicated, but if you kind of understand the way to define it, it's actually not that hard. Okay? So these polynomials, addi and multi, we call it varying predicates. And from the name, you can see that they're actually related to the addition gates and multiplication gates, right? So taking this addi as an example, it is taking three labels, three inputs, G, U, and V. And G is a label for the gates in layer I here. And then U and V are labels for gates in layer I plus 1. Okay? And then this polynomial outputs 1 if and only if these three gates connect to an addition gate. Otherwise, it always outputs 0. Okay? And again, you can actually see why this equation holds through a simple example, right? You're going to try this output wire, V00, as I showed you in the previous slide. Okay? So you're going to ask, what is add I for this G equals to 0, and then U equals to 0, 0, V equals to 0, 1, for example. You can see that this add I becomes 0 because there's no addition gates connecting to that output, right? So there's no add term in this summation at all. Only mod I can become non-zero because of this, it is a multiplication gate. So then you're going to iterate through all possible binary inputs. What is V0, and then this U equals to 0, 0, and V equals to 0, 0. Mod I equals to 0 in that case, because that is not the connection to a multiplication gate. And among all these kind of binary inputs in this summation, there's only one term that evaluates to 1, and that is 0, 0, 0, and 0, 1. And that corresponds to this multiplication gate. And because of that, this summation simply becomes V00 equals to V100 times V101. That is exactly the same equation as I showed you before. Okay, so you can see that by iterating through all possible binary inputs, we are kind of replicating this equation for all the gates in this layer. And that is why this equation holds. Okay, so with this equation, we can actually apply the Soundness protocol. And that gives a way to reduce the correctness of summation to the correctness of the evaluation of this function at a random point with logarithm proof and logarithm verification time. Okay? So the kind of the high-level flow of the Soundness is as follows. So the prover sends a claimed output to the verifier side, which is not trusted, and that's why it's marked in red. From the output, the verifier is going to define a multilinear extension V0 and evaluate it at a random point R0. Okay, and then by the design of the GKR protocol, V0 can actually be written as a Soundness equation of V1. Okay? So because of that, we are going to run the Soundness protocol. And at the end of the Soundness protocol, the verifier needs to evaluate this V1 R1 in this equation. Okay? And instead of evaluating on her own, we're going to ask the prover to send this V1 R1 to the verifier. And by running the Soundness protocol, the guarantee is that as long as this V1 R1 is correct, so does V0 R0 and the output. So it's a reduction of the correctness to one layer above. Okay. So then we're going to do this layer by layer, right? So in each layer, the verifier is going to run the Soundness protocol with the prover to reduce correctness to V2 R2 all the way to VDRD in the input layer. Okay, and the guarantee again here is that as long as this VDRD is correct, so does everything else, including the output. So how do we check that this input evaluation is correct? In the original GKR protocol, because it's delegation of computation, there's no secret. The verifier actually knows the input. So the verifier can actually evaluate this VDRD on her own and then check that it is the same as this last message in the GKR protocol. And that completes the whole reduction and guarantees that output is actually computed correctly. Okay, so that is the key idea of the GKR protocol. So here I actually have a slide for the all the steps in text, but I'm not going to repeat it here. So just rephrasing all the things I said in previous things in text instead of a picture. Okay, so then with that, the complexity of this GKR protocol is in each layer we are running a proof, a Soundness protocol. So the proof size is the order of d times logarithm. It's linear in the depth of the circuit, but only logarithmic in the width of the circuit. So that is why it can actually be sublinear in the size of your computation. The verifier time is also order of d times login, plus the time to evaluate this evaluation for the input, and the time to evaluate this multivariate polynomials li and multi. In the worst case, this can actually be linear in the size of the circuit. But for many structured computations, like matrix multiplications, the parallel circuits, this can actually be reduced to order of d times log n, because these are actually public. These are only depends on the circuit description, but not on the values in the circuit. And also, if you allow pre-processing, you can also actually compute these things, verify the computation of these things from the prover in time order of d times log n. Okay. And the soundness follows the Sumcheck and the Schwarzschild lemma. Again, is not relying on any cryptographic assumptions. So that's also kind of outstanding property in the literature. Okay, so that completes the description of the GKR protocol. So I think I'm going to skip this part about the prover time, but just the short message here is that you can actually apply this dynamic programming together with some new techniques in our paper called Libra to reduce the prover time to linear in the size of the circuit. So that is actually optimal. So to sum up, GKR protocol is a delegation of computation, and it can actually be turned into a zk-SNARK, allowing the secretiveness with polynomial commitments and the Fisher-Shamir transformation. And the prover time with this new algorithm of dynamic programming and the Libra paper, you can actually achieve this optimal prover time, linear in the size of the circuit, with the proof size d log n and verifier time also d log n. Star denotes that it depends on the structure of the circuit. Okay. And overall, this line of SNARKs has outstanding prover efficiency in practice because of these optimizations I mentioned in the literature. But of course, the drawback is that the proof size is usually relatively large. So yeah, that's everything about my talk. And thank you for listening. And now I'm happy to take questions.
Thank you very much, Yupeng. Let me just remove the stream for now. Yeah, so in the questions tab, we've got a few questions. Let me know if you can see those, and I'll let you address those questions.
So I'm not sharing my screen anymore, right?
Feel free to, if it helps out, to answer the questions.
No, I mean I need the screen to see the questions. So let's see.
I don't think you're sharing your screen anymore, so you can tap back to the live storm event to see the questions.
Oh, okay. I can see the chat, but
I can read the questions out for you. There's a questions tab next to the chat.
Oh, okay, okay.
Let me know if you can see those.
Oh yeah, I can see it now. So I'm going to share if I need to refer the slides, but I'm going to answer the questions one by one now. So the first question is how GKR differ from bulletproof, and then what are related algorithms to GKR and Sumcheck. Bulletproof is well, you can say that very broadly the recursive structure shares some similarity, but in terms of protocols, they're not related at all. So bulletproof is more of a, they call it using homomorphic commitments like the Peterson commitments or bilinear pairing. You can actually do this round by round reduction to reduce it to a smaller size. So that relies on the features of the homomorphic commitments. And this is actually a separate SNARK scheme or polynomial commitment scheme. And then what are the related algorithms to GKR? Again, all these GKR algorithms are field operations, and bulletproof you actually need group operations in bilinear, Libet curves for these things. So I don't see any kind of common developments of these protocols. Okay. Next question is: Do these multiple rounds ensure soundness or completeness, or both? Yeah, this actually both. So while I'm describing these protocols, I'm basically talking about the completeness. So this is basically the honest version of the prover, and as long as the verification output accepts, so it is complete. But actually, the more challenging part is reasoning about the soundness. And I sketched the idea for the Sumcheck protocol, but feel free to refer to the paper or some online blogs about the reduction? And the answer is yes, it's actually guaranteeing both. And the next question is it necessary or even normal for SNARKs to have a sublinear complexity with respect to input? Oh, yeah. So let me see. Yeah, so there are kind of some, I would say, some historical kind of reasons or developments. So there are two lines of work that's kind of combined right now. So one line is on zero knowledge proof, like NIZK, non-interactive zero knowledge. If you want zero knowledge, then you don't need, well, it is already non-trivial, even if the proof is not sublinear and the verifier is not sublinear, because you're guaranteeing the secrecy of your witness. Okay, but there is also another line of work called verifiable computation or delegation of computation, or even if you're saying SNARKs. Okay, so for that one, if all the inputs are public, then in principle the verifier can actually compute the result locally in linear time. Okay, so then if your proof system only has a linear proof and linear verifier time, it's meaningless to use it as a delegation of computation. So that is the reason why for those schemes, in order for them to be meaningful, we want sublinear verifier and sublinear proof size. But now both schemes are actually combined into the same umbrella of zk-SNARKs. Of course, there are kind of debates on different assumptions and techniques, but under the umbrella of zk-SNARKs, we actually want both. We both want zero knowledge and also sublinear proof size and sublinear verifier time for critical applications. So because of that, it's actually better to have sublinear complexity with respect to input. Okay, so hope that answers your question. And then the next one is, could you explain the basic idea behind Sumcheck and GKR? So that relies on the Schwarz-Zipper lemma, random challenges, right, as explained in the talk. So every round you're kind of reducing this claim about the larger sum into a smaller sum, and the key connection there is a random challenge of the two polynomials. So the Schwarz-Zipper lemma says that for two distinct polynomials, if you evaluate them at a random point, the probability of the evaluation being the same is negligible. It's the degree over the size of your sample space, which is can be made negligible if you sample uniformly from a large finite field. Okay, so and then because of that, you're reducing this problem to half of the size and half of the size until a small instance. So that's the idea behind Sumcheck protocol. And the GKR protocol is further building on top of Sumcheck. And then for a layered arithmetic circuit, you're just trying very hard to write the relationship from the previous layer to the next layer as a Sumcheck equation. And then you just apply the Sumcheck layer by layer to reduce it to the input level. Okay. So the last question is, what are the bigger ideas that leads to the linear complexity compared to earlier protocols? So this one probably I can share you the slides that I didn't have time to show. Yeah. So the key idea or the main difference is, where is mine? Yeah. So the major problem is we're going to run the Sumcheck protocol on this complicated equation. You don't need to read all the details, but the main thing you need to notice here is this add and mod. And the simple fact is there are 3 variables in it instead of 1. Okay. So then if you apply the original protocol, dynamic programming technique, you get a linear prover time in the size of the multilinear polynomial. And what is the size of this polynomial? There are 3k variables in it. So the size is 2 to the 3k, which is n cubed. So that is why the original protocol runs in cubic time. And of course, other works reduce it to out of n log n using sparsity and so forth. But the key idea of this Libra paper is we can actually break it down into 2 steps, phase 1 and phase 2. In each step, you can actually write it, this complicated equation, into the product of 2 multilinear polynomials in the Sumcheck. And then we also propose an algorithm to initialize these 2 multilinear polynomials into the evaluation of the Boolean hypercube in linear time by a linear scan of the gates in the circuit. So combining these 2 steps with the dynamic programming, we can actually generate the proof for this Sumcheck protocol in this phase in linear time. So it's a product of 2 multilinear polynomials initialization in linear time and then dynamic programming in linear time. And then after that, you're going to do it again in a different type of product of two multilinear polynomials in phase 2. So combining everything together, you have a linear time prover. And that is the key idea in this Libra paper over the previous papers. Okay. All right. So yeah, I think that's all the questions I can see here. Are there any other questions?
Great. I think that's all the questions. Let's give people. Did you answer the terminology question? What's the difference between a lemma and a theorem mathematically?
Oh, I didn't see that question. So, I mean, I guess it's not quite related to this talk, but usually theorem is a more of a major statements in the paper, and lemma I'm usually using it more for the kind of prior results and then the derived equations in the paper. But don't quote me on that. I'm not mathematical expert to give a rigorous answer for that.
Great. I think that's all our questions and all we had time for. I want to give a big thank you, Yupeng, for a great lecture today. If people have questions, are they welcome to reach out and you can send some answers over?
All right. Yeah. Thank you very much. Thanks
Great.
for joining.
Amazing. Well, thank you very much. And for everyone on the Explore Expander Bootcamp, we'll have another workshop at 6 o'clock UTC or UK time coming up. So yeah, thank you again once more for joining us, Yupeng, and we'll see everybody on the next workshop later today. Goodbye.
Thank you. Bye.